All right, welcome back, guys. So we've made it to the last chapter in this course, Chapter 9. We cover two sections, 9.1 and 9.2. So 9.1, guys, is on what's called correlation. So you may have heard this before. What we're going to be looking at is if a change in one thing, if there corresponds a change in another thing. Of course, we're going to call them variables. Anyway, we're going to see if that's significant. You've probably heard the phrase correlation is not causation. Okay, so we're going to talk about that some as well. So just because two things are correlated doesn't mean that one is causing a change in another. Okay. All right. Let's go over these objectives. So we're going to learn an introduction to linear correlation. Now, there are other types of correlation. Okay, I want to point that out, but the only thing we're going to look at is linear correlation. And then the difference between an independent and dependent variable, and then the types of correlation. And then furthermore, how to find what's called a correlation coefficient, how to test a population correlation coefficient, rho. This is another Greek letter, okay? And it's spelled RH. I'll write it RHO, okay, and it's pronounced rho, using a table. And then how to perform a hypothesis test for a population correlation coefficient, and then how to distinguish between correlation and causation. Although I don't know that we actually talk all that much about this, that last learning objective. All right. Well, anyway, when we talk about correlation, guys, we're talking about some kind of correspondence between two variables. Okay. And lots of times data can come as ordered pairs. And so you could have the x variable, which we'll call the independent variable, and then another data value, we'll call it y, okay, and it's the dependent variable. Okay, so you're probably familiar with ordered pairs from algebra previously, so this is really the same thing. Okay, so you could be collecting data such that, you know, x represents the amount of time spent studying for an exam, and then y could represent the actual grade on some exam. Okay, and then you can see, as you can imagine, those two variables would be correlated. But anyway, that's kind of what we're doing here. And you probably also remember x being called the independent variable in algebra. That just means that a change in x would cause a change in y. Because in algebra, we said that y was a function of x. In other words, y depended on the value of x. And so that's why we call y the dependent variable. Okay. All right, well, let's look at this first example. It says identify the explanatory variable and the response variable. This is just terminology that reflects the same thing. Okay, instead of calling a variable the independent variable, you can call it the explanatory variable. And then instead of calling it the dependent variable, you call it the response variable. It's the same thing. So it says a farmer wants to determine if the amount of precipitation received by similar crops can be used to predict the harvest of the crop. Okay, so all we're trying to do here is figure out which one is the independent variable, which one is the dependent variable. So guys, just think about it this way. Crops tend to depend on precipitation, right? So the actual harvest, that would be our dependent variable, and the amount of precipitation received, that would be the independent variable. Okay, so let me write this. So the independent variable, which typically we use x to denote that, would be the amount of precipitation I'm just going to abbreviate here. And then the dependent variable, okay, y in this example is going to be the actual harvest, okay? And typically you would be measuring these things. So these are typically numerical values, guys. So you would have a specific amount of precipitation, it could be in inches of rain, and then you would have some sort of unit in which you measure the actual outcome of the harvest. Okay, it can be in bushels of whatever, corn, wheat, whatever crop it is that you're measuring. Okay. All right. So let's take let me say another thing. If you think back to one of our previous lectures when we were talking about ways to display data, the scatter plot, guys, is what's used to graphically display data that comes in pairs, okay, or that has this ordered pair relationship, x, comma, y, okay. And so by looking at a scatter plot, it's not very mathematical, but you can, just from the way the ordered pairs are scattered, you can get a sense or a feel for if there's a correlation there or not, okay, between your independent and your dependent variables. So that's what we're going to look at next, some examples. All right. So I've got 4 different examples here. This first example, this scatter plot, well, before we talk about it, your values of x, or the independent variable, they're typically plotted on the horizontal axis, okay? So just like in algebra, the values of x are going to be on the horizontal axis, and then values of y are going to correspond to the vertical axis here. And so if we had collected some data, okay, from two different variables, and we plotted all those ordered pairs, and we got something like this, this would be what's called a negative linear correlation. It's linear because all these points tend to make up a straight line. Now, like I said, there are other types of correlation, but we're not going to be concerned with those in this course, okay? So what this means, guys, is that increases in the value of x would correspond with decreases in the value of y. And so that's why these points tend to slope downward, or in other words, they tend to form a downward sloping line, okay, something like this. And if you recall from algebra, a downward sloping line has a slope that's negative. So this would be an example of negative linear correlation here between two variables. And then to the right here we have an example of positive linear correlation. So this just means that as values of x increase, values of y, or values in your dependent variable, they tend to increase as well. Okay, so the variables basically do the same thing. And then down here we've got an example of a scatter plot in which there's not really a correlation. Okay, these points, they don't really form a coherent line. And then finally, this would be an example of nonlinear correlation. So there is definitely some correlation here. And if you recall from your algebra classes, this would be like a quadratic correlation. Okay, and the shape of this looks like a quadratic function. So anyway, but like I said, we're just going to be concerned with linear correlation in this section. Okay. All right, we'll continue. All right, so up here, I said, well, it looks like there's a correlation here. There's a correlation, positive correlation over here, but how do we quantify that? And as you guys know, math is very precise, okay? So we need a way to quantify the correlation, or in other words, try to figure out how tight Well, we call it goodness of fit, essentially. In other words, how tight or how closely do these points cluster around some imaginary line, okay? And the tighter that fit is, then the stronger the correlation. Okay, so we have a way to quantify that. We use what's called a correlation coefficient. Okay, and we give it the name of R. So I want to point out here that R will represent the correlation coefficient of the sample. And then rho, which I mentioned above, rho is the correlation coefficient of the population. Okay, so there's a difference. Okay, it's the same thing like X bar is the mean of your sample, and then mu represents the mean of the population. So again, guys, the parameter of the population we don't know. Okay, so we rely on a sample. Okay, and so from a sample you would obtain a correlation coefficient R. All right, well, let's look at some of these characteristics associated with R. Yeah, so we don't want it to be, we want it to be quantitative and not qualitative. So we're going to use a precise numerical measure, and we're going to call it the correlation coefficient. Okay, and the range of the correlation coefficient is going to be anywhere from -1 to +1 inclusive. That just means that it can actually be -1 or +1. All R is, guys, is the slope of the line. Okay, and then if you look at this next bullet point, when X and Y have a strong positive correlation, R is going to be close to 1. So that makes sense, okay, because we saw an example in which there was a strong positive correlation right here. So an imaginary line through all these points would have a slope close to 1. And then when X and Y have a strong negative correlation, then R is going to be close to -1. And then finally, if there's no linear correlation, R is going to be close to 0. So that would be evidenced by this scatter plot right here, okay? And then this one, R would be close to -1. This one over here, R would be close to +1. It wouldn't be exactly -1 or +1 because these points don't form a perfect line. But we're going to look at some examples now. Now, in the real world, if you're just collecting data, from two variables and you're trying to figure out if they're correlated or not, in the real world, you're never going to get 1 or -1, okay, most of the time. But anyway, let's look at some scatter plots here, or some relations between two different variables. So if you look at this first one here, what this scatter plot represents, the independent variable is the number of adult movie tickets purchased, okay? And then Y, or the dependent variable, is actually the total cost. So you know intuitively the more movie tickets you buy, the higher the cost. So there is a direct relationship there, or correlation. And only in this instance, guys, would you actually get a perfect positive correlation. Okay, and that's what we see here by these points. Each of these points, or ordered pairs, represents an actual ticket, okay, or an actual purchase. So see here, this point represents 2 tickets purchased, and then the corresponding cost or price, and etc. for the rest of these. So this does actually form a perfect positive linear correlation. And so in this case, your correlation coefficient would be exactly 1. Now this next example, our two variables are height, that's our independent variable, and then our dependent variable is shoe size, okay? And so we got this scatter plot from the data, and so you can see that this is not a perfect correlation, but it does appear as the values of X increase, the values of Y are increasing as well, or more generally, the taller a person is, the larger the shoe size they're going to typically have. Okay, and we can sort of see that evidenced. These points are kind of clustering around a line sort of like this, but this is not a perfect linear correlation. That's what I want to point out. But now if we were to quantify this, we might get something like this. The correlation coefficient of 0.81. Okay, so that's actually really strong in the statistical world. A correlation coefficient that high or that close to 1 is actually very, very strong. So you can say there's a very strong correlation between an individual's height and then his or her respective shoe size. And then here we see a relationship between two variables that's not as strong, that's relatively weak. Okay, so here we've got the income per year in thousands of dollars, and then the amount spent on milk. Okay, so you'd be trying to figure out, is there a relation between an increase in income versus an increase in milk consumption? And it does look like there is sort of a correlation. Okay, now it's not a real strong one. The more widely scattered these points are about this imaginary line, the weaker the correlation. Okay, so you can see the points over here, they form a perfect straight line. These, not so much, and then these points are scattered even farther away from this imaginary line. Okay. And then down here, guys, we've just got some examples with negative correlation. So this would be like the number of questions that you miss on a test and your corresponding score. So the more questions that you miss, the lower your score, right? So there's a negative correlation here. And it has a correlation coefficient of -1. So for example, if you were taking a test and every single question was worth 5 points, well, for each question that you miss, your score goes down 5 points. Okay. And then here we see another example in which this is a very strong negative, because this is very close to -1, -0.92. Number of absences, and then test grade. So there is a correlation between the number of absences, and any teacher will tell you this, and really any student, I'm sure, would know this as well. The more you miss, the less likely it is that you're going to have a high test score. Okay. And then lastly, this scatter plot, there's really not a correlation here at all. And the two variables would be the person's IQ score and then their corresponding height. So intuitively, you would expect there not to be any sort of correlation between those two variables, a person's IQ score and then their actual height. And this scatter plot is kind of evidence of that. And if you look at the actual correlation, it's really close to 0. Okay. All right, well, those are some examples, guys, of some different scatter plots between two variables and then the respective correlation coefficient. Now, you may be wondering, well, how were these correlation coefficients calculated? And that's actually a fairly complicated procedure, and this is actually the formula that you would use to find it. Okay, fortunately for you guys, you're not going to have to use this. So if you look at this formula, you can see, this Greek letter sigma here, meaning there's a sum. We're summing a lot of different things. And really what's going on when you're finding R, guys, is you're finding all the little deviations. So if this is my imaginary line, what you're doing is you're trying to figure out, well, how far is this point from this line? How far is this point? How far is this point? Okay, so you have like negative deviations and you have positive deviations, and then you sort of try to find an overall or sort of an average deviation. On average, how far away are these points from this line? Okay, so it's similar to finding the standard deviation with a data set in which you're just looking at data from one variable. So it's a very similar thing here. So you can see up here, you know, because these points are farther away from the line, those deviations are a lot greater, okay? And so because of that, we have a correlation coefficient that's closer to 0. But anyway, fortunately for us, we're actually going to rely on the calculator to find this value of R. Okay, so when we have a sample and we have data for two different variables, we're going to enter those in two different lists in the calculator. We're going to let the calculator sort out how strong that correlation is. Okay. All right, and that's what we're going to look at now with example 2 here. So the two variables that we're looking at are age. Okay. So these different values would be our different values of x, our independent variable, and then the corresponding vocabulary size. These would be the values for y. And intuitively, you could think that, well, we should see, there should be a correlation here, right? Because as a person, well, these values for x are relatively small, so we're really just talking about children. As a child gets older, you expect their vocabulary to also increase. So we would expect, or I would expect, a positive linear correlation here. Okay, so I would be expecting a value of R that's positive and maybe, you know, relatively close to 1. All right, so I'm going to show you how to do this. We're going to do it using the calculator. Okay, so you're going to enter your data just like you always do in the list. And I've actually already done this, okay, so as not to take up so much of your time. So you're going to come over here to the stat key. Just going to go to edit again. And then I'm missing a list too, guys. So what I did is I put the values for my independent variable age under list 1. And then I put the values for my dependent variable vocabulary size under list 3. Okay. Now we need to tell the calculator to basically perform this formula on all of this data. Okay. So the way you do that is you come over here to stat and you go to calculate, similar to the way you go to one variable statistics. Okay, but you scroll down to number 4 where it says linear regression, and you hit enter, and then whichever list you use for your x values, you just make sure you've got that list in here, and whichever list you used for your y values, you want to have that one. And to access these lists, guys, there's a couple ways to do it, but the easiest way is just to hit second and then the corresponding list. So list 1, list 2, list 3, etc. And then all you need to do is just come down here to calculate, hit enter. Well, this is not giving us R. Let's see. Oh, I know, I'm going to the wrong thing. Alright guys, I think I know what's going on. Yeah, so we're doing it the right way. You've got to make sure there's a diagnostic feature when your calculator turned on. Okay, so let me see here. You come over here because if it's not turned on and you go to this linear regression, it should be giving you the value for R, and it wasn't. Okay, it's just giving us values for A and B. We'll talk about these in the next section. So what you need to do is come down here to catalog. So second catalog, and then you need to scroll down to D for diagnostic, and then it will give you the option to actually turn it on, if I can remember. Here it is. Yeah, so see, I think by default it's turned off, so you need to come down here and click enter to turn it on. So click enter again, and when it says it's done, whenever you do that linear regression, again it should give us the value of R. So let's try it again. Come over here to calculate, go down to number 4. I'm using list 1 and list 3 again. There we go. Okay. So it also gives us R squared. We're not really going to talk about that, but it does give us R. So this is the correlation coefficient. And if you notice, not only is it positive, it's also very close to 1. Okay, just like we suspected. So let's actually write it down. So R is equal to 0.97. I'll carry it out to 3 decimal places. Okay. So guys, there's a positive linear correlation here, and it's a very strong. I mean, it's almost perfect. You could even do a scatter plot if you wanted. Okay. Well, yeah, let's go ahead and do this real quick. Come over here to stat plot. Let me turn this on. And enter. Now I need to change my X list to list 1. You don't necessarily have to be able to do this. I just want you to see the scatter plot. And then all you should have to do is hit graph. Well, I've got another function in here. I need to clear that. I'm going to go to zoom. And zoom stat. There we go. Okay. All right. So this is, so you can see these values of X, and then you can't, these values for Y, they're wide ranging, so you can't even see the demarcations on the Y-axis. But anyway, if you look at these points from this scatter plot here, you can see this is forming a pretty straight line, okay, because we have a near perfect positive linear correlation here. But anyway, and you can see some of these look black, and that's because there's actually 2 probably hitting right here, and 2 here, and 2 here, so they're so close. But anyway, we're going to say a strong correlation, or near perfect, really. And so in the context of this problem, this just means that as an individual or as a child ages, so too does their vocabulary size increase, okay? Almost perfectly linearly. So, anyway. All right. So the last thing we're going to talk about, this is not an extremely long section. So let's say this was a sample, okay? And that's what this is. This is a sample. What if we want to hypothesize about the population? Well, we can't sample every single child and then determine their corresponding vocabulary size. So we take a sample like this, and we look at this correlation coefficient, and then we compare that. We're going to use a table. We're going to compare that to a critical value that we're going to obtain from a table, and that's going to tell us whether our correlation coefficient is statistically significant, okay? All right, so testing the population correlation coefficient rho. So like I said, the correlation coefficient R is just a sample statistic. So what we want is to extrapolate from our sample statistic to the actual population population correlation coefficient rho. And so we're going to compare the absolute value of R to a critical value from what's called a Pearson correlation coefficient. So this word Pearson just comes from a famous statistician, okay? And then we're going to make a decision about rho. So this is basically how you do it, guys. Determine the number of pairs of data in your sample, or in other words, your sample size. So in this last example, our sample size is 11. And then you're going to identify your level of significance, so alpha. So typically it's going to be 5% or 1%. You're going to find the critical value using the table, and I've got the table here in the notes, okay? These are going to be the different critical values depending on your sample size, okay, and also your level of significance. And notice, guys, notice how these values are significantly higher for this stricter level of significance, and that's what we would expect. And then finally, to decide whether the correlation is significant, you look at the absolute value of R and you compare it to the critical value in that table. So if the absolute value of R is greater than your critical value, then you say the correlation is significant. Okay? That's a conclusion that you make about the actual population. All right, so let's test this with that last example. So here, our sample size was 11. Okay, so if I'm looking at 11 right here, these would be my two critical values right here, depending on my level of significance. So you can tell that the absolute value of our test statistic, or well, not test statistic, but sample statistic here, is much greater than either of these two values. So we would say this one is statistically significant, okay? And the actual value for alpha with a correlation coefficient this strong would actually be minuscule. All right, well, let's try one of our own. So you will have to refer to this table, okay? So example 3, what we're doing here is, it says this table shows the heights of 8 high school girls and their scores on an IQ test. So what we're trying to figure out, is there a correlation between between a girl's height and her corresponding IQ score? Well, based on that previous scatter plot example that I showed you right here, we're probably going to say no. Okay. But let's try this one anyway. So our first step is we've got to know what the correlation coefficient of the sample is. Okay. So again, before starting this video, I actually put that data in here in my calculator. And guys, you can use Excel for this as well. Just put your values for your independent variable in one column, your values for your dependent variable in the second column, and then just select both of those columns, go to your statistical package and select linear regression. And you should be able to do it in Excel as well. All right, well, I'll just show you real quick. I'll put my data in lists 4 and 5, okay? And so what I'm going to do is go back to Stat and go to Calculate, go down to number 4 for linear regression, and make sure I put list 4 for my values of X, and then list 5 for my values of Y. And come down here to Calculate. We're going to get a value of R, and look at this one. It's negative, but remember, we're taking the absolute value of it. But look how close it is to 0. So that suggests there's really not a correlation at all, just as we would suspect. But let me go ahead and write this down. So R is equal to negative 0.00, I'll say 64, okay? So now, to actually, well, in part B it says describe the type of correlation, if any, and interpret the correlation in the context of the data. Well, this is so close to 0, guys, I'm going to say that there is no correlation. Okay, but what we're going to do now is actually declare whether statistically this is significant or not. And we're going to use this value of alpha. Okay. 1% essentially. So we're going to look back at that table. Our sample size, put this in the notes, n is equal to 8. Alpha is 1%. We're going to go back to that Pearson correlation coefficient table. And we're going to find that critical value. And if the absolute value of R is greater than that critical value, then we can say that there is a correlation between these two variables. But if it's not greater than R, then we conclude that there is no correlation. So let's see. Let's come back up here. So here is 8 for our sample size, and here is the corresponding value at that particular level of significance, 0.834, okay? So I'm going to say from table, R is equal, or absolute value of R is equal to 0.834, okay? All right, so what we have to do is compare the absolute value of our correlation coefficient that we obtained from that sample to this value right here. This is our critical value from the table. Well, this one's pretty obvious, right? This is definitely less than 0.834. And because of that, we conclude that there is no correlation. So see, guys, at this particular level of significance and with this small of a sample, our correlation coefficient from the sample would have to be bigger than this, and this is pretty significant, okay, before we can conclude that there's an actual correlation between a girl's height and her corresponding IQ score. All right. Well, that's basically it. Like I said, this is a fairly short section. Most of this you're going to be using your calculator for. So anyway, in the next section, guys, 9.2, what we're going to be doing is actually saying, okay, well, if there is a correlation, what's the equation of a line that best represents that data? Okay, so like, just real quick, right up here, correlation between these two variables. What would the equation of this particular line be? So, in other words, we're deriving a function, and that's why all that work that you did in your algebra classes is so important, because in the real world we collect data, and we do a regression. That's what it's called, and we come up with a function, and we can use that function to make predictions, but it's only as accurate as our data, okay? So anyway, that's kind of what we'll be doing. We'll be trying to come up with a function that models or predicts this trend or this correlation between these two variables. Okay, guys, so until the last section,